Okay, now we will move to our third step, that is generating the modulated signal, modulated waveform. Okay, so I think so you can already so we have generated our encoded signal. Okay, the encoded signal. Okay, so we have this kind of pulse train. Okay, so we will have this kind of pulse train like this. Okay, after generating the line coded signal. Okay, then we can before uh, before feeding to an antenna, we have to do the modulation. Okay, we have to do the modulation. Okay, so in this course, in this lab session, we are mainly focused on, okay, we are mainly focused on BFSK, BPSK, and Qpsk. Okay, uh, for these uh, for these modulation schemes, for these three modulation schemes, we are going to focus our attention. Okay, so let's take this BPSK. Okay, so let's take this BPSK. So this is binary phase shifting. I think you already know the concept. Okay, so in binary phase shifting, the you have a sinusoidal signal. Okay, so your sinusoidal signal will look like this. In amplitude, okay, cos 25 FCT plus alpha. Okay, so this will be your carrier signal. Okay, this will be your carrier signal. Okay, so this is the carrier frequency. This is the carrier frequency. Okay. So this frequency should be in um, RF range. Okay, RF range. Okay, so you know that in Sri Lanka for 900 GSM 900, if this signal is GSM 900, we are using 850 to 960, as I can remember, this bandwidth. Okay, so you can use a frequency within this bandwidth. Okay, for 3G. Okay, 3G we are using 2001 megahertz. This is megahertz. Okay, and for 4G we use 2600 SLTs. SLT. Okay, this is for SLT 4G network, LTE network. Okay, this and this frequency. Okay. So so this FC can be changed. That is changed according to your system. Okay, so so you know that. Okay, so if we simply look, okay, you know that if you have one, okay, so here you have a signal like this. Okay, signal like this, 1010, so on. Okay, go like this. Okay, yes. Okay, so I think you already know this. Okay, to explain, if you have a bit stream like this. Okay, so you know that to achieve the BPSK transmission, we should have one basis function. We should have one basic function. Okay, so you can verify it using the Graham-Smith orthogonalization procedure. No, I think you have learned this. Okay, so actually this is our basic signal. Okay, so in BPSK you can use this sinusoidal signal as your basic signal. So basic signal will be xt a cos, okay, 25 FCT plus 5. So here we are, this is the amplitude, this is the frequency, and this is the phase. Okay. In amplitude modulation, we are going to change the amplitude. In frequency modulation, frequency shifting, we are going to change the frequency. And in phase shifting, we are going to change this phase. Okay. Okay. So here BPSK means binary. That means two PSK. Okay, that means we will use only two symbol. Okay, two symbol means you can send one bit through one symbol. Okay, so here you can send 1 and 0. Okay, 1 and 0. Okay, so you can assign this 5 is equal to 0 for 1. Okay, and so your signal will be xt. Okay, let's say it is x1t. It will be a cos 25 FCT. Okay. Then for 0, you have to use a phase shift. Okay. So normally you will use 5 phase shift, 180 phase shift. Okay. So your second signal will be a cos 25 FCT plus 5. Okay. So you know that cos 25 FCT plus 5 is minus cos 5 2 FCT. Okay. So it will be minus cos 25 FCT. Okay. Actually, this is your basic function. No? This is the basic function. Okay. So you have to use only one basic function. Okay. So now we have to generate this in MATLAB. Okay. So if we generated the signal, if we generate the signal, it will look like this. Okay. It will look like this normally. So so here for 1, it is 0 phase shift. So it will start here and it is like this up to this time duration, up to this time duration. That is the bit duration. Okay. Then uh, then if it is 0, there is a uh, 5 phase shift, 180 phase shift. So it will start here like this. Then it goes like this. Okay. And if it is 1, then it is start here. Okay, so on. So this the signal should look like this. Okay, then how we can draw it in MATLAB? Okay, so that is a question. Okay, now we are going to do the modulation. Okay. Okay, so I think actually very simple method is there. Okay, so you can see that the the benefit of this code actually. Okay, what is the benefit of this code? Okay, actually you can see that okay, here here you see that we assign a value, constant value to this array. Okay, and again we assign a constant value to this array. Okay, so we will assign some constant value with the duration. Okay, so I think this 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 code can be easily modified to generate the modulated signal. Okay, to generate the modulated signal very easy. How? Okay, please stop this video and try to figure it out how we can do it. Okay. Okay, I will continue. Okay, so please try to do it with yourself before watching this section. Okay. So my idea is that okay, I think it is not in the same manner in your lab sheet. Okay. Uh, so actually that is my own code. Okay, so maybe most probably it will not included in your in your lab sheet. Okay, lab sheet. Okay, I think it use another method. Okay, yeah, I think it is another method. Okay, so I think you better try to understand this method also. Okay, and I think you can use my method also, no issue. Okay, so what I'm going to do is, you can see that here for this value we assign constant value. Okay, so that we can generate a generate a digital signal like this. Okay, so what happened if I so you can see that this id is equal to 1. Okay, this id is equal to 1, so id is equal to 1 when this so this mid, that means any value of message signal. Okay, so it is equal to 1, we put 5 here. Okay, we put 5 here. Okay, so all value will be 5. Okay, and if that message signal value is equal to 0, we put minus 5 here. Okay, so all value is minus 5 for this nj matrix, nj array. Okay, so to write the code very simply. Okay, what you can do is, you can simply uh, you can simply assign the assign your cosine signal here, no, cosine signal here, then it will calculate the corresponding cosine value and it will plot. Okay, then you can generate the uh, waveform without a problem. Okay, so let's try to do it. Okay, actually it is working because I have tested it. Okay, so I have no doubt. Okay, it is working. Okay, so you can see that so I take the same code. Okay, and I think I need this value also. Okay, I need this value also. I think you can get the same value. Okay, no issue, because yeah, you can get the same value. Okay, because uh, so after this loop is after executing this loop, the program will look into this loop. Okay, then again it calculates this id and t again. So it will not generate any crash, I hope. Okay, uh, so when I test it, I use different variable. Okay, so I think we can use the same variable. There should not be a crash. Okay, because so after after finishing this, after executing this session, this loop, the program will come to this loop. Okay, then it calculates the values again freshly. Okay, and you can see that in both case the t value will be same. T value will be same. Okay, okay, t value will be same. Okay, so you can use the t in the same value. So if your t are different from, if your t values here and t values here are different, you have to use another variable, two variable, otherwise it will crash. Okay, but here the t values will be in this range and t values in this range, so we can use the same variable. Okay, so now I just assign my carrier wave here. Okay, I just assign my carrier wave here. Okay, so let's take let's take this the a is as 10 volt, a is 10 volt. Okay, and fc is maybe 100. Okay, so let's take this like this. Okay, so it is 10 volt and ufc is 100. Okay, so I plot it. Okay, so this nj I have to change. Okay, so I will so it is my pass band signal, no, so I will modulated waveform mw. Okay, so that means my modulated waveform. and I have to put the index here because it map the value using this index. Okay, so I have to use this index. Okay, so now I can write it as 10 into cos, okay, to 5 FC. Let's say FC has 100 T. Okay. So, okay. And here, if it is if M, the message bit is not equal to 1, it should be 0. Okay, it should be 0. And if it is 0, we have to put minus a cos 25 FCT signal. Okay, so I think this will work, no issue. Okay, okay. So what happened to that plot? Okay, so here I have plot. So here I'm going to plot my. Uh, I'm going to plot my. So I will remove this scaling. Okay, time scaling. I will remove that time scaling. Okay, so so here this is my line coded signal. Okay, so now I am going to plot uh, plot my modulated waveform. Okay, so modulated waveform information are in this array. Okay, so it is also the independent variable is t. Okay, it is MW, the dependent variable is MW, modulated waveform. Okay. And I will color it in blue. Okay, so I think if I run this, it should be fine. I think I have to write the hold on here. Okay, otherwise it will not show this plot. Okay, so if it is there, so here a problem. What happened? So this said that the number of elements in B and I must A, I, B. Okay, A, I, B means this one and this one. Here. Okay, so this is array and this is also array. No, so this T value should be same. Okay, so if I put TJ here, I think it is solved. Okay. It will be okay. And I have to put the hold on here. Otherwise, let's see what happens. Mm, you can see that here also we have this thing. Okay. So you can see that here we use this blue MW for this array. Okay, so that array also it map the same value. Okay, this 111 it map here 111. Okay. What's happening? First thing is I have to put this 0. Okay, because you see that because if 0, I have to I have to I have to I have to generate minus cos 25 FCT value. Okay, so I think it will not be an issue. Okay, it will not be an issue anyway. We will check. Okay, so let's check what happened to our issue. So if we take this MW value, okay, so you can see that every point 10, 10, 10. Okay, check this T. Okay, I will use 4 beats. Okay, otherwise it will take many times to many. It will take long time to simulate. Okay, 4 beats. Okay, and then maybe this. Okay, let's reduce this up to some level, because maybe this signals this signal will be too speed to plot. Maybe let's check now. M is equal to 4. Happen to yeah. So I have to put n here. Okay, otherwise it will try to get the other value also. Okay, so here also I have to put 10. Okay, because now we have only 4 values, no, m up to 4. Okay, but here if I define them up m in the j up to 10, it it going to calculate M5 value. So when M5 is going to calculate, there is no M5 value, no, because the maximum value, we have only 4 values in M. Okay, so you can understand it. Okay, so you can see that here only 4 values. Okay, so these 4 values is okay. When it, so here I put it up to 10. Okay, then it calculate M10, M5. So M5, when it go to this stage, when the ID is 5, he checked M5. So there is no value in M5. So it give a error message. So okay, so I have to put this up to N. All the this one also up to N. Okay, that means up to 4. Okay, if I write this on this, now I think uh, we okay, because in last time, okay, so you can see that we are calculating value by substituting. Okay, so you can see that now it is somewhat okay. Okay, so if we reduce the frequency, I think we can see it more clearly. Okay, because actually in that case the frequency is very high. Okay, so that the 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 signals we can't visible clearly. Okay, now I think you can clearly see it. Okay, so you can see that this is, so I put 6 here. Okay, I put 6 here. Then I think it will be more clear. Okay. So all are 1 1. Okay, because you can't. So you can see that the all are 1 1 1. So you can't see the variation very properly. Okay, so I will put. Okay, I will comment this. I'm not going to use. I'm not. You will get confused. Okay, I will run it again and tell you. Okay, now you can see that we have 0 0 0. Okay, so so up to here we have 1 0. Okay, so it is starting from minus side. Okay, like this. Okay, and again 0. It is started from like this. Again 0, like this, like this. Okay, so I think the signal is okay. No, so here we have a phase shift. Okay, and if I put 2 here, I think it is more clear. Okay, because we have 2 more lines again. And I think I will take so here when I'm going to randomly generate bit, it can be 1 1 1 1 0 0 0 0 0 0 1. Okay, so we can't see the variation very properly. Okay, so I just comment this. Okay, and I generate a message signal like this. Okay, so I generate a message signal. I directly generate a message signal like this 1, 0, 1, 0. Okay, so I have generated this 1 0 1 0 message signal 1 0 1 0. Okay, so that I can observe the changes very clearly. Okay, so if I write this, so here I just put so now you can see that, no? So here we have 1. So it is starting from here. Okay. Then up to here, it is 1. Okay. So then it is 0. Now the phase should be reversed. Okay. Now it is starting from here. Okay. Now this is the phase. Okay. The 0. Then again it is 1. Okay, that means the 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 signal should start from here with zero phase. Now it is going to like this. Okay, here it is again zero. That means it should start at -6. Okay, like this. Okay, so I think you can generate the signal in this way, very easy. Okay, so I think you can generate the uh, frequency modulated signal also very quickly. Okay, uh, because the only thing you should do is in for frequency shifting we need two basic function. Okay, we need two basic function. So one is higher frequency. Okay, let's say it is 4. Okay, and other is a lower frequency. Let's say it is 1. Okay, let's say it is 1. Okay, so if you have run this, I think you can get the frequency shifted key signal also. Yes, I think it is okay. No, for 1 you have a high frequency. For 0 you have a low frequency. Again 1 you have a high frequency. For 0 you have a low frequency. Okay, so this can also be generalized to generate a Qpsk waveform. Okay, please do it by yourself. Okay, so the hint I can give you a hint to generate Qpsk signal. You need to have you need to have four symbol. Okay, four symbol. That means you need to have two basis function. Okay, and also uh, you have to compare. So here I have compare only one bit. Okay, only one bit, but you have to compare two bits here. Okay, the first bit ID and maybe ID plus one, the second bit also. Okay, and if that first bit and second bit, if the first bit equal to 0, second bit equal to 1, you have to assign one phase. If it is 1 and 0, you have to assign another phase. If it is 0, 0, you have to assign another phase. If it is 1, 1, you have to assign another phase. Okay, so I think you can do it by yourself. Okay, think how to do this and try to do this. Okay. Okay, so I think we have discussed how the signals are generated. Okay, the modulated signals and line coded signals. Okay, so now, so I think we also have to see the bit error performance of the modulation schemes. Okay, so we will see it.